Okay, so it's really a great pleasure for me to introduce the next speaker, Luís Orozco from the University of Maryland and the Joint Quantum Institute, that besides being a really, really great researcher and professor, he has done a lot of promotion of physics in Mexico and helped a lot of the development of physics here. So it's great to have you.
Okay, thank you very much. But I don't know if I should thank the organizers, and particularly Karina. I really shouldn't thank her for bringing me here, but that's okay. She's forgiven, right? Anyway, so there was a debate, and the English won because Eduardo convinced me that I should give it in English. Okay, so for those of you who have not, who have difficulty with the language, you can find this version of this talk in Spanish over there. Okay, so just take a picture of the website, and then you can download it there. It's in Spanish. All right. So I thought that it would be very, very, very useful instead of giving you a lecture about the recent experiments that we've done. Because this is a workshop, and there are many decisions that you're making right now about what you're going to be doing and how you're going to be doing it in the future. This is what you're going to be doing as a workshop, right? I think I will remind you that I wish I knew what I'm going to tell you now, 30 years ago, when I was deciding on one platform over other where to invest my life. Okay? So let me just, the last two lectures that we heard touch in many of the points that I'm going to tell you again. So the first thing that I want to remind you, because all of you know it very well, is what happens when one atom interacts with light in free space. And so Einstein told us that there are three possibilities. What are those three possibilities? The first one is the atom. You see, there is light coming in, the atom is in the ground state, and it gets excited. And that's what we call absorption. Then, once the atom is in the excited state, it can decay, and that's what we call spontaneous emission. And then there is the inverse process of this. Please note, just apply time reversal to this, which means I enter with one photon, I put the atom in the excited state, and I get two photons outside. This process, stimulated emission, is the inverse of absorption. It's the classical part. The quantum part is this jump. The quantum part is the spontaneous emission. That's the genius of Einstein in putting that extra element to get the statistics. Everybody knew about these two processes, but it took an Einstein to say, no, we're counting wrong. Spontaneous emission is where the quantum is. This is forgotten many, many times. It took me a while to realize that one is the inverse of the other, although I read it, but you have to understand with your guts. Okay, so I hope that, these processes are very, very, very important. Is that what we're going to be talking about, okay? So, the next thing that I want to remind you is what is a cross-section. The cross-section is really the shadow. It's just the shadow, right? It's as if the shadow that an atom, literally a dipole, we don't need to talk about dipoles. You don't need to quantize anything. You just talk about dipoles and you get exactly the same result. What is the shadow that a little antenna, which happens to be an atom, will cause on a beam of light, right? So it will absorb a certain amount of that light, and that area is basically the wavelength squared divided by 2, because 3 over pi is 1, right? So that's the shadow. And now, again, everybody has heard and knows very well the interaction. The interaction that we're going to be talking about in most of quantum optics, in most of quantum information, is always a dipole interaction. And the dipole interaction, as you know, a little dipole, whether it's classical or it's quantum, You learn this in electricity and magnetism. It tries to align to that electromagnetic field, right? So we have the dot product, right? So, and of course it can be aligned or it can be anti-aligned. But if you put it like that, good luck. You've done nothing, right? Now, here comes the first subtle point that I hope all of you will follow. So, here's a dipole, and this dipole is an antenna. So what is the best antenna that I can make? Well, that's the question you have to answer when you're designing an experiment. What is the best? So the nature gives us a natural antenna which is in the different energy levels of the atom. And we saw already in the first lecture that that is an operator. And this operator is between two energy levels, right? This operator is between two energy levels, and it's an operator which is odd. In the case of, I can replace that and calculate that with the wave functions and everything else, but you can do a very, very, very accurate back of the envelope calculation and immediately say, come on, it's going to be a few Bohr radii. And yes, it is. You see, it's 4.22 times the charge of the electron times the Bohr radii. So now, you have seen in the corridors that some people are talking about, let's do experiments with Rydberg atoms. Why should I do Rydberg atoms? What is the size of the dipole of a Rydberg atom? A Rydberg atom is really a planetary system. And now the electron is enormously going around very, very far. Okay? It's going into that. Now, you over there, what do you see? You just see a dipole going back and forth, right? My hand is the electron going around, but you see just going back and forth. So the reason why there is a lot of interest in the Rydberg systems is that the dipole moment, this guy over here, right? This guy over here is very, very large. Compared to here, it scales with a very large number. So watch out. So there are papers in the corridor about Rydberg states. There's a local expert here, right? This guy. And he can tell you a lot more about that. But also you know that the amount of energy that a photon in the microwaves carries is not very good. So you have to balance things, all right? So I do want to remind you that this shadow, we usually measure it by measuring the attenuation. What in engineering and in optics we call the Beer-Lambert law. So that's the attenuation of an intensity of light as it passes through a medium, and that medium absorbs, and you see that cross-section there? It just depends on the cross-section, and it depends on the density of that gas. So what are the units of this? Inverse length. So that's why the attenuation is always given to you in centimeters. All right? So, again, Pablo already talked to you about the rate of decay. Fermi taught us very, very correctly that the decay rate is always dependent on only two things. The first thing is the interaction. So you have to have an interaction in order to have a decay. What kind of interaction? Well, it's up to the problem that we have to see. And the other part is usually forgotten. The decay products have to end up somewhere. That's the phase space. If you don't have where to put that photon, it's not going to decay. Put an atom in a box whose length is less than lambda over 2 in all directions. Will it decay? No. There is not a mode there. You've affected that by changing the phase space. But you can also change the interaction. So you have two knobs, right? There are two knobs, and they're very, very important for you to understand. Now, Pablo showed you what the result is in free space, and in free space, we end up having that omega cube over there, which is pretty dramatic, if you want. Now, there is one more number that will enter in the discussions that I want to bring in, and that is the saturation intensity. And the saturation intensity, as I defined it in this case, is simply, I'm going to give one excitation every 2 lifetimes into the cross-section of the atom. So you can see it's a power per unit area. And it's typically 1 milliwatt per square centimeter in the allowed transitions in alkalis. Okay, so that's the, so if the lifetime is very, very long, this changes. If, but this also works in the microwave or whatever. You're going to have a smaller amount of energy that the microwave carries, but you're going to have a much larger, right, cross-section, right? There is a cross-section, the lambda square, all right? From this saturation intensity, we can normalize in the lab something which we call the Rabi frequency. And the way we normalize it, look, is the interaction energy. And that interaction energy, we say simply the intensity that we have divided by the saturation intensity because it's a field, and then we just multiply by the gap. Okay? Under these circumstances, the excited population, you can see when you take the limit of the intensity going to infinity goes to 1/2. So let's just start talking a little bit about cavity QED. Cavity QED is literally quantum electrodynamics for pedestrians. What does that mean? That means that I don't have to worry about the divergences that or the infinities that we encounter in quantum electrodynamics, because we're going to limit ourselves to a finite number of modes, maybe 1 or 2, but then it's okay. The rest we can treat in a different way. And we may have one atom or so you have an atom and a cavity. And there are usually 2 regimes, and I'm going to only say a few things about the non-perturbative regime, where the coupling is much, much larger than the dissipation. That's really what we want. So what is the coupling? And let's go now to the coupling. So what was the interaction? The interaction is between the dipole and the electric field. So it's the dipole and the electric field. What is the electric field that we're talking about? So the electric field that we're talking about is the electric field that you associate with an intensity of 1 photon. Okay, if I have an intensity of 1 photon, what is the electric field? It is a pity that we are getting used to not thinking about fields, but it's fields that we quantize. So don't come to me and say it's a photon. No, it's the field. It is the field that we quantize. Okay, so but you know from electricity and magnetism very well that the electric field square is an energy density. Yeah, remember that? There are some epsilon zeros floating around and they are written correctly there, but you know that the electric field square, that's how you write the Lagrangian for the electromagnetic field, right? The electric field square is an energy density, all right? So I can calculate what is the field associated with an intensity of 1 photon. So here we have, that's the energy, right? And what is the density? Well, the effective volume of the mode. Right? That's all there is there. So now, this is a very nice thing, and I saw it in the slides of the first lecture. How large is this for a photon indivisible in a cavity which is about 1 millimeter in length, and for a cross-section which is about 30 microns? It turns out that it's something that all of you, I hope, have sensed. It's about 9 volts per centimeter, which is what you get if you put a 9-volt battery with your tongue and touch it like that. Can you feel that? And if you haven't done that, do it. You will not die. But please, so that tells you that a single photon can have an enormous electric field. It's of the order of a few volts per centimeter squared, per centimeters, okay? So let's try to see what happens in cavity QED. I'm talking about optics, and you will see at the end, I will move away, right? So these are visible. If we talk about microwaves, that's not going to be the case, because the frequency of a microwave is 10 to the 9, while the frequency in the visible is 10 to the 14. You have 5 orders of magnitude. Then your electric field is going to be the square root of that, those 5 orders of magnitude, right? So let's give you 2 orders of magnitude. I'll give you the work in tens of units. Okay, so that gives you an idea. So you get 2 orders of magnitude less. But nevertheless, look, these are millivolts per centimeter. This is something that is perceivable, right? So if I have just a cavity, an optical cavity, all of you know that you have on resonance transmission, and there is a Fabry-Perot, here's a Fabry-Perot, and the amount of light gets enhanced inside the cavity, and then it leaks out. But what we really want to do is we want to put an atom there. So if I put an atom there, then I'm going to have coupling between the atom, the dipole moment of the atom, and the electromagnetic field. Fine, that's the coupling. What is that going to do? That's going to be able to absorb it and then to emit it again. Pablo said that, oh, it just goes back and forth, back and forth. Unfortunately, from time to time, I lose that to the sides. You see, there is a loss over there. And of course, there is a loss as it goes out of the cavity. To be a little bit more precise, the cavities that one usually uses are asymmetric. And what's the reason? The reason is that the detectors are on this side, and if the transmissivity of this mirror is equal to the transmissivity of that mirror, then half of the information goes this way, half of the information goes that way, and that you lose half of the data. So if you close this door, as we did, to about 5 parts per million, and you open this door, actually that should have been 200 parts per million, then most of the information gets out in that direction. Okay? So, and as I said, that didn't get translated, so it's about 7 volts per cent. Okay? All right, so let me introduce you to a number. It's a number that should become the guiding point, a very, very important guiding point, whenever you are trying to design an experiment in quantum optics, in quantum information. This is going to be the figure of merit for the graduate students. This is going to tell you how fast you're going to get your PhD. There's one other number that you need to know to get your PhD fast, and that's the signal-to-noise ratio, right? Your signal-to-noise ratio. And that, unfortunately, has a square root dependence on the time you take to get your degree. So if you increase, so be careful about that, okay? All right, so the cooperativity, as it's defined here, is the ratio, if you want, of the good coupling between the atom and the cavity to the losses. You see? That's, so what you would like is to close the gates, right? And then everything goes well. Well, that's a little bit of a mistake, because then you cannot get your PhD. You have to let the system leak out some information so that you can take data and eventually graduate. Okay? So it is always a compromise. You cannot say, no, I am going to just decrease, I'm not going to have this. Well, you have to somehow figure out a way to extract the information, all right? And when I have n atoms or n dipoles in general, what I have is not the cooperativity of 1, but the n times the cooperativity. So there is a very nice enhancement that we get if we have n atoms. And you'll see it used later on, all right? So just because I want to show you a couple of plots. They are plotted in terms of the dimensionless input and output, the transmitted and the incident fields. They are just fields, please note fields. They are related to the saturation intensity. So what's happening in steady state in cavity QED? So we're injecting field, and a little bit of field is going out because I have an atom. And that atom the electric field induces in the atom an atomic polarization. And as you know, on resonance, the atomic polarization, the reason why light is absorbed, you learn that in electricity and magnetism, is that there is at the dipole that gets induced is exactly out of phase, right? So there is destructive interference in the forward direction, but there is no interference in the sideways direction, and that's the origin of the fluorescence, right? So you have here comes the electromagnetic field, the dipole starts to oscillate, it sets up a field of its own, but it's out of phase with that, and these two guys, that's what I try to illustrate with this cartoon, they cancel each other, and the transmission in the field is highly attenuated, you see, by the number of atoms in the field. However, a more interesting thing that happens is, what happens if I actually look at the dynamics? And what's happening is that the excitation can be in the field, or it can be in the atoms. It can be in the field, and it can be in the atoms. And at what rate is the field going from the excitation going from one to the other? Precisely at the coupling constant. And the coupling constant for n atoms increases by square root of n. Great. So what happens at very, very low intensity? At very low intensity, these are two coupled oscillators. Why? So look at what happens in an experiment when I try to measure the transmission of a cavity, but I showed you a moment ago in frequency space. Right now, I am showing you how a cavity decays. All I am doing is I'm turning off the light, and it decays exponentially, and here is what you see, right? So I am looking at the decay of the cavity. It's a beautiful exponential decay over a few decades, and that's it. You take the Fourier transform, and that gives you the Lorentzian. Now, the question I have for all of you is, now if I put the atoms inside, what will I see? Well, what I see is actually oscillations. But these oscillations are very peculiar. So the oscillations don't surprise me because they go at the beginning, all the excitation, I am only measuring the escaping light. I am only measuring the escaping field. So the excitation is in the field. It goes down, but remember what I said, that there was a polarization opposing. So the electric field has disappeared, but there is an enormous polarization, and that enormous polarization is this guy. And then that can go back to the field and the cavity and back to the field, and this is the exponential decay. And this is all very, very nice. You saw it a moment ago, both with Pablo and with the first lecture, and that's the James Commons Hamiltonian for you, which is telling you that we have an energy in the cavity, we have an energy in the atoms, and we have an interaction, right? If you want to add dissipation, you have to add reservoirs for the cavity, reservoir for the atoms, and they have a rate of kappa and gamma in 1/2 speed. Really? Okay, so again, going back to what happens, I have the ground state, and the ground state here is extremely boring. There are no excitations. You see? The atom is in the ground state, there is no excitation in the field, right? But when it gets interesting is if I put one excitation, I really don't know, and they are coupled. I really don't know, and here are the two levels that now show the symmetric and the anti-symmetric normal modes that you learned when you saw the two coupled oscillators, right? That's these two guys. That's those two guys. And those two guys are quite interesting because you can immediately see that this state, if I manage to create this state and let it live for a long time, it's entangled. This state is entangled between the field in the cavity and the atom. If I know that the excitation is in the cavity, I know immediately that I am in the ground state. If I know that the excitation is in the atom, there is nothing in the cavity. Okay? Now, the Fourier transform view of these oscillations is, of course, the vacuum gravity splitting. All right? Good. So more about coupling an atom to a cavity mode. All right, so here we go. So the problem that we have is an atom that it is in a cavity and it's decaying. And as you see, it can decay in the right mode, that's the 1D. It can decay in another mode, those are the radiation modes. And the total decay is that. However, because this can be changing, the presence of the cavity, and you'll see, can be changing the boundary conditions, can be changing the mode, can be changing the interaction, doesn't have to be the same as in free space. So the enhancement of such coupling is defined as the ratio of this decay to what you had in vacuum. The efficiency of the coupling is the ratio of what we have into the mode that we're measuring, the one-dimensional mode, compared to all the other decays. Now, some of you may have heard about the Purcell factors, which is what I told you about the enhancement or suppression just by geometry, and it is really just the ratio of the alpha and beta. It's the total radiation compared to what you have in free space. So if you're building a laser, you really want to have these very large, right? So that the total radiation is much, much larger than in free space, okay? And here comes another way to look at our friend, the cooperativity. You see, the cooperativity is what is going into the right channel compared to what is going into the wrong channel. Doesn't that look like quantum information? You want all the information to get out in gamma 1D. For that, you need to make this number as large as possible. Okay? That's exactly this number is equivalent if you put it, but it gives you a different insight. And I find that it's much better to have 2 or 3, and here is a third form to represent it. So the third form to represent it is really just the cross-sectional area of the dipole divided by the cross-sectional area of the mode. So if you want to see a transit of Venus across the sun, Venus better be sufficiently large compared to the light of the sun, right? That's really what this says. Now it's much nicer to have a lunar eclipse, right? Because then the cross-section of the moon can be about the cross-section of the sun, and if you're in the right place, it will be completely dark. Now, this object here tells you how many times you go through the sample. So if you are Venus, but you go many, many, many times because you have mirrors, so you see you go back and forth, then the probability of absorption increases. So I presented to you these 3 things. I presented the enhancement, the efficiency, and the cooperativity. But let's stick to the cooperativity. And the cooperativity, as I say, and I want to spend a little bit here, is how do you choose a platform? This is the figure of merit. So you see, let's just say I really want to do it in, for example, I really want to do it with optical transitions. Well, you know that in optics it's very, very difficult to get something of the order of lambda squared, right? The modes of the electromagnetic field in a cavity are very seldom of the order of lambda squared in area. They are more like hundreds or thousands of lambda squared. So that puts you in big trouble. So now you can see why in the experiments that we've done with my former students, these 1 over t ends up being 1 over 10,000, right? Sorry, 1 over is 10,000 because it's 1 over 0.0001, okay? Because we wanted this number to be of order 1 or larger. Okay, so as I said, this ends up being your choice of atom is really almost completely gone by the time you say, well, I'm really going to try to use the smallest area possible, which would be lambda square over 2 or something like that, all right? So then you have a problem here, and then it's the other parts of the technology. Another thing that you can think of is let's try to maximize the coupling constant. And by trying to maximize the coupling constant, remember what did we do? We needed to increase the energy density, right? The energy density, so the volume is very small, so we need to get a very small area. It's the same thing that you're trying to do there, okay? Minimize the volume. However, what happens if you do not have a cavity? I saw lots of experiments here do not have a cavity. Do they have any hope? The answer is yes. Why do they have hope? Let's go back to here. So the people that are working with glass cells, with an atomic gas, you see they have a transmission of 1. They don't have a cavity. And what do? They hit the cell. Why do they hit the cell? To have a very large number of atoms. All right? But they still are stuck with these two numbers, the cross-section and the area. Now, is it better to work with cold atoms? Is it better to work with warm atoms? Here are the numbers that are going to tell you which way to go. Okay, so if you have the possibility of having a very control beam, extremely narrow and extremely uniform and non-diffracting, well, you better use all your atoms in that place. Use a cold sample. If you don't have that, hey, just use a hot sample, all right? So you can have, and the problem, as I said a moment ago, can be diffraction, okay? So let's go to the next thing. So why don't we try to fix the diffraction problem? So what do we have to do? What we have to do is we have to guide the mode. That way, once I focus to about lambda in dimensions, lambda square in area, it doesn't diverge. In free space, you know, you focus and it immediately diverges. In this other case, you can guide it, all right? And I'll tell you a little about photonic structures, and I'm not going to tell you, unfortunately, about plasmonic structures, except very, very hinting in a moment. So now let's go from cavity QED to waveguide QED. So now you see the problem in this cartoon. This comes from the PhD of Jonathan Hood. So if the area of the cross-section of the atom is much, much less than the area, you're not going to have an eclipse there, right? The amount of disturbance that you're going to have is extremely small. And it is the interaction what is going to give you the possibility to do a quantum computation or to do whatever. Now in the cavity, what you do is you basically have the same situation, but you pass many, many, many times. So effectively, which is a solution that happened in the laser, the gain is too small, just go through many times. But there is the other possibility, which is to use a waveguide, where the area of the mode is comparable to the cross-section. Where the area of the mode is comparable to the cross-section. And the waveguide that I'm going to refer to is exactly what Pablo introduced, which is the optical nanofiber, and you'll hear Neil tell you something in a moment. We have a waist of about 500 nanometers. The dimensions are, just so that you have an idea, are of the order of 100 human hairs. Sorry, 100 nanofibers fit across a human hair. Those I do not have, right? So what happens in the optical nanofiber is, at the beginning, the mode is completely confined in the core, And as it propagates and goes through a taper region, it starts to leak out. And the very, very interesting part is here, because most of the light actually is in an evanescent field outside. And because it's an evanescent field, you all remember that wonderful 2 pi that you have to put in the case is e to the I k dot r. But now that number is imaginary, so you end up with e to the minus k dot r, and k happens to be 2 pi over lambda. So that means that the length scale over which this guy decays is not lambda, but is lambda divided by 2 pi. So the length scale goes, in our case, from 780 nanometers to about 150. And the modes look like this. The fundamental mode looks like this. It's an HE11. These are Bessel functions. These are not Legendre-Laguerre. This is inside the fiber. And then for higher order modes, they have very, very, very funny polarizations. This looks like a quadruple polarization. All right? So again, let me remind you that what Fermi taught us. So now we have to do the calculation and see that, you see, we're going to affect the decay because the density of modes changes, but also the interaction has a funny shape. Why does it have a funny shape? Because the electric field are these Bessel functions and not a plane wave. These Bessel functions that are decaying, they are decaying, okay? So the idea is to put an atom, as I was telling Scott, yes, we put it about 30 nanometers away from the surface, right? We put them outside there, and now these guys can talk. And these guys can talk, and they can decay, right? And what we want to do is see how they decay, and you'll see that the definitions are exactly the same. So, as you remember, coupling enhancement is a comparison of what goes in the direction I want to what happens without the nanofiber. Coupling efficient tells me what goes in the direction I have compared to all the decays. Purcell factor is the ratio of the two. There it is. And cooperativity is indeed the same. Here is something for you to remember, because this is going to facilitate your PhD, right? Why? Because it is the ratio of what goes into the selected mode where you're taking the data compared to all the rest. And you want to take data all the time, don't you? Nobody told you that you have to sleep. If your professors told you you have to sleep, that's not good. Okay, so now the cooperativity. Let's go. Now, there is a subtlety now that I do want you to pay attention, is that because of the presence of a nanofiber, it gets, the original definition that I had gets modified by an effective index of refraction. This is some kind of average of the mode. Remember, part of the mode has an index of refraction, and part of the mode does not have an index of refraction, right? So that one needs to put that. So what happens if I put a photonic structure? So here I hope you remember a little bit of your knowledge already of condensed matter, and the dispersion relation of a uniform waveguide needing a nanofiber is just linear, right? And you know that the index of refraction is related to that slope. Now look at this. If I engineer the shape of this photonic structure, I can open a band gap. And if I open a band gap, look at the dispersion relation. What is happening now to that slope? The slope is tending to 0. What does that mean? Well, that means that the excitations are going to be not moving very fast, right? The photons cannot move. This is worked on at Caltech. They call it the alligator photonic waveguide. And these are details. It's an incredible piece of engineering, and you can see they wanted to trap the atoms right here. This is the cross-section over here, right? Where the area of this mode is incredibly large. And in such a way, they would be able to put the photons will not move. They would just rest on top of them. So that's a very, very nice dream. It hasn't worked. It's up to you to make it work, right? You don't have a PhD. You want to do something really good, right? So let me finish by asking the following question. I've been telling you how to plan an experiment, but is there a limit in this actual case? How much can we do this? What's the coupling of the atom and the electromagnetic field in the case of circuit QED? Okay, this is a very, very beautiful article by Rob Tronkoff and Steve Gerving, where they calculated in an extremely simple way what would be the coupling constant between a dipole of dimensions d with characteristic length L, right? They can make that dipole with just a little antenna with superconductors, and they put it in a coaxial cavity of length λ/2. So again, what we need to calculate is what is the energy of a single photon in that cavity. Well, the energy of that single photon in that cavity is actually covered by the effective volume. But remember, the radius of a coaxial cable is extremely small compared to lambda, right? You use it for something at 1 megahertz, and 1 megahertz are many, 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 many meters. What is the diameter? That's maybe 5 millimeters. So now you can see what happens. What happens once you rearrange all this and just compare the coupling constant to the frequency of the dipole. It's only limited by the fine structure constant. So there is a limit, and that limit is about 7.07 of the length divided by the radius, which I told you, right? So the length divided by the length of the little antenna divided by the radius. So that is going to be of order 1, right? So the vacuum Rabi splittings that I was showing you before were a megahertz, 10 megahertz out of 10 to the 14 hertz. So that's 10 to the 7 to 10 to the 14 is 7 orders of magnitude. Here is 10% of that. So for those of you theorists, I think it's an extremely interesting problem because the James Cummings model is no longer valid. You are going to have all sorts of things that you have to take into account. And with that, I would like to just remind you that you should look at the figures of merit of your platform. You really, really should look, and I hope this little, if you want, overview of many, many things that you had seen and heard here and there, and I try to assemble together to give you a thing, is useful so that you can get your PhD on time, all right, and on budget. And with that, thank you very much.
So thank you very much for that great talk. Questions?
So at the beginning of your talk, you said that if you had known 30 years ago what you know now, you would have done things differently. What would you have done differently?
Very, very good question. Probably the thing that sidetracked me the most, right, was the idea that the key part, if you just look at the definition in terms of G's, right? That it was the volume and not the area. That's exactly what I think. And what would I have done before? Different. So I went for smaller and smaller cavities. But what I should have figured out is that things like what Jonathan Simons does nowadays, using the cavities very close to the concentric place, you can get extremely small areas. It's a little bit unstable, but you can survive. And that's the key part. And Vletic, I was very glad to see him the other day, they are going exactly the same route. You don't need to go to a small
cavity, you need to go to a small waist.
You need to go to a small waist.
Yeah.
So that's probably my most honest answer. I say, no, but it's going to be unstable. No, you try that. You're just not, you shouldn't go there. You shouldn't go exactly to concentric, but just a little bit away from concentric to gain stability, but you can get extremely small areas. And it really was much later that I was like, come on, this is just the area of 2 cross 2 areas. The rest is gone. So that's it.
Another question?
Scott.
Yeah, that was really beautiful. Thank you. I'd like to hear more. So I want to, maybe you can show the QR code again at the I will listen in Spanish as well. But you mentioned plasmonics. Did you? Maybe that was related to the Sholkoff?
Yes, because you have that metal is what allows you to get the mold so confined.
Okay. So in that case, I guess, relating to Bill's question, does it still come back to, because the plasmonic cavities can have crazy small volume, 10 nanometer cubed kind of volumes. So does it still come back to area in that case?
Yes, it does. That's where you gain. You gain in the area. The other is going to be of the order of lambda. It's really the area. If you want, my thing was not to think of the area.
All right, thanks.
There was another question?
Look. Wait. Someone who's not being...
Professor, how is that possible to put one single atom in a cavity or in a neighborhood of a nanofiber?
So you can develop a trap which will sustain and maintain one single atom inside the cavity. Now, if you ask me how would you do that trap, you can use an ion trap. And then you basically have the ion trap for days, months. If you use an atom, we tend to heat them a little bit as we interact, and you may have to, what you end up doing is a protocol in which you turn cooling and trapping and alternate, and that can work. What kind of trap? As a successful trap, you see, you have a fabric Perot cavity there. So you can see, because it's a fabric Perot, there are standing waves, right? And in a standing wave, you have regions of very high intensity and regions of very low intensity, right? So if the wavelength of that light is detuned to the red side of resonance, the dipole will feel a force that will take it to a very, very intense place. So the little tortilla that you have at the center will work extremely well as a trap. Okay?
Okay, so I'll repeat the invitation of Neil. Come and approach the speakers and talk to them, ask questions. And with that, I would like to thank Luís and the other speakers of this session.